Unit 9 and Unit 10.
10 and 11.
Yeah, I was like,
yeah. Alrighty, guys. Let's continue talking about rates. So hopefully you guys remember how to do rates, but let's look at this problem. We're gonna be writing rate laws and rate constants again. Okay. So here we have a problem where it says ozone in the upper atmosphere is depleted when it reacts with nitrogen oxides. The rates of the reaction of nitrogen oxides with ozone are important factors in deciding how significant these reactions are in the formation of the ozone hole over Antarctica. So basically, when humans release nitrogen oxides, they react with ozone, and then we lose that ozone layer that we are told is very important. Okay, and one such reaction is down there, where you have nitric oxide, NO, reacting with ozone to form nitrogen dioxide and oxygen gas. Now, here it's asking us to find two things, the rate law and the rate constant. Now, if you guys want to look back at your notes, just remember that the rate law is going to equal K, and then the concentration of the reactants to a certain power, okay? And then those, if you have 2, there's 2, and then if it's 3, there's 3, okay? Okay, so what I want you guys to do right now is to write the general rate law for this reaction. You're not gonna have the exponents. Just put M and N for the exponents, but take about 30 seconds, write the rate law for this reaction. Okay, if you wanna check back at your notes, you can. But write the rate law for this reaction, and for the exponents, just put M and N for now, okay? Alrighty, guys, let's write the general rate law. So if you guys remember, again, just to remind you guys, rate law, okay, so the rate is equal to K, which is the constant, the reaction constant, or the rate constant. We're gonna have to write the concentrations for the reactants. The first reactant is NO, so it's gonna be the concentration of NO. We don't know the exponent yet, so I'm just gonna put M. And then the other reactant is ozone, and we don't know the concentration or the power yet, so we're gonna write N. Okay, so this is what you should have done. Now, the problem is asking us to write the entire rate law, so we're gonna have to figure out M and N using the data that we have here, okay? So if you guys remember, the rate is dependent on how it changes based on the reactant concentration. So what we're gonna do is we're gonna start comparing the data that we have here in order to find out how changing the concentration will affect the rate, okay? So again, the rate depends on the reactant concentration, but also the exponent. And so what we're gonna do is we're gonna use the data here to figure out, hey, if I change NO, how is that gonna affect the rate? If I change O3, how does that affect the rate? That's what we're trying to figure out. And that will give us the exponent, okay? So let's take a look at the first trial. The first trial has 1 times 10 to the negative 6 for NO and 3 times 10 to the negative 6 for O3. So what you want to do is you always want to hold one thing constant, right? Because if I don't change one of the values, that value is not going to affect the rate at all. So if you look at trials 1 and 2, it's going to have the same value for the NO concentration, right? So if you guys notice, the rate changes, right? But the rate changes because the concentration of O3 changes. It doesn't matter. The NO doesn't play a role here because it's not changing. It's constant. So if you guys take a look at the concentration of O3 and how the rate changes, let's just look at this. What's the difference? What's the relationship between trials 1 and 2? How did the concentrations change?
Concentration increased from trial 1 to 2.
Okay, yeah, it increased. Okay, so this is going to increase. But specifically, how did it increase? Yeah, times 2, right? It doubled, right? So the concentration here doubled. Okay, so again, you guys don't need to copy down the table or anything, but just write that. Trials 1 and 2, the concentration of O3 doubled. Okay. So I'll write that right here. If O3 times 2, then rate. Okay, so if we take a look at the rate, how the rate changes, how much does the rate change? Yeah, it's also about times, not exactly times 2, but actually it is like exactly times 2. Yeah, times 2. Okay, so if O3, the concentration doubles, the rate will also double. So what is the exponent for O3? Okay, so let's think back to our exponents. Okay, let's say, for example, our concentration of O3 is 2, okay? If I double it, what happens? It goes to 4, right? But let's say it's 3 and I double it, what does it go to? 9. Okay, so if you guys take a look, or if I go to 4, let's go a little bit more, it becomes 16. So if I double, so here it's saying if the concentration of O3 doubles. So if I double it from 2 to 4, what's the relationship here? Yeah, times 4. Is that what we see here? No, because if I double the reactant concentration, it quadruples here. So it can't be 2 because that means you're squaring it. Does that make sense? You guys look super lost right now. Okay, so let's rewind. Okay, so you guys, we all know, or we can all tell that if I double the O3 concentration, the rate also doubles, okay? So let's just use numbers that are a little bit easier to look at, okay? So if I say the O3 concentration is, let's just do 1. Okay, if I square 1, right, it becomes, the rate is gonna be 2. Okay, so this side is gonna be the rate, and this side is gonna be the concentration. Okay, and right here we doubled O3, right? So if I double 1, what's the doubled concentration? 2. But if we say that the exponent is 2, what's going to be, oh my gosh, the rate will be 1. What's going to be the rate if I, yeah, 4. Yeah, so it can't be, the exponent cannot be 2, because if the exponent is 2, then we're going up by times 4, not by times 2, right? So here, what does the exponent need to be? 1. It's going to be 1. So this is what we talked about very briefly last time. But if the exponent, so if m or n is equal to 1, it's going to have the same, okay, it's going to have the same relative increase. Okay. That's why if it's times 2, the rate goes to times 2. If I triple it, it's going to go times 3. Okay, it's going to have a 1-to-1. It's going to have the same relative increase. Okay, so the exponent for O3 is 1. It's kind of annoying, huh?
Okay, so like the middle part, since it's a times 2 and the right side's a times 2, it's basically trying to get the middle to match the right.
Exactly, yeah. It's going to have the same relationship.
Okay.
And it has to be a factor of 1.
So then if it was going to be times 2 in the middle and then times right on the right, times 4 on the right,
Then it would be 2. Yeah, exactly.
uh,
Yeah, so this is why I'm saying the algebra really starts kicking up a notch with these latter units. It starts getting a bit more trickier. Okay, now we want to find the relationship for NO. So we're going to hold O3 constant. So if we look at trials 3 and 4, O3 is going to be constant, right? So if we look at how the concentration of NO changes, how does the concentration of NO change? Yeah, it doubles. Okay. So if the concentration of NO doubles, what happens to the rate? Yeah, it's also going to double. So the exponent is going to be 1. So this is going to be your rate law. This is the answer to A. So basically here, the rate is going to change with the same correlation with how the concentrations of the reactants change. Okay. Okay, now we got to find the rate constant, which is K. Okay, so now that we have the rate law, we can calculate K. So what you're going to do is you're going to use this rate law, and you're going to use the numbers from one of the trials to calculate K. So let's pick trial 1, just because it's the first one. So we're just going to plug in the values. What was the rate for trial 1?
0.6.
Yeah, exactly. Times 10 to the negative 4 is equal to K. The concentration of NO for trial 1 was 1 times 10 to the negative 6 and to the power of 1. And the concentration of O3 is 3 times 10 to the negative 6 to the power of 1. Now, if I put anything to the power of 1, it doesn't change the number, right? It's the same exact value. So I can ignore the power of 1s. So I'll give you guys a minute, try to calculate out K. You can punch it into your calculator. Hopefully you have one that can do exponents and things like that. It'll make it a bit quicker and easier. Thank you. All right, maybe another 30 seconds to finish up calculations. See if you guys can get the units of measurement too. That's a lot of fun. Oh, I hate rates. This is my least favorite unit of the entire year.
There's no jokes.
It's not. It really isn't. It was only in the beginning when we talked about dating. Yes, I guess we could talk about digestion. Alrighty, guys. So let's reorganize this equation. So if we reorganize everything here, what we can do is we can isolate K by just dividing what's on the left, the rate, 0.66 times 10 to the negative 4 molarity per second. We can divide that by the values that we have on the right. So we can put 1 times 10 to the negative 6 molarity and 3 times 10 to the negative 6 molarity on underneath it. Okay, so this is the operation that you should have done. Now, for the units, we know that one of the molarities cancels out. And so we're going to have seconds on the bottom of a fraction and molarity on the bottom of the fraction. So your units of measurement should have been molarity -1 and seconds -1. Okay, and then if you punch that into your calculator, you should get 2.2 times 10 to the power of 7. Okay, everyone got that? Let me know if I'm wrong, because the other day I was crazy and I was writing insane things. Okay, so the value for K is going to be 2.2 times 10 to the power 7. That's how you can write the rate law using some experimental data. And that's also how you can solve for the rate constant. All right, any questions on how we solve that out? Hopefully not too bad. Again, the algebra really does pick up. So just make sure that you are comfortable using exponents and seeing how they can relate to things. Okay, so if we take a look at this rate law, what order of reaction is this? Yeah, second order. It's going to be a second order reaction. And again, it's because we have an exponent of 1 and 1. 1 plus 1 is 2. So it's going to be a second order reaction. Yeah. It's going to be to the power of 7. All right, so what we're going to do now is we're going to look at how the units of measurement change depending on what order the reaction is. Because let's say, for example, this was a 2, okay? That means I would have to square everything inside, right? So down here would not just be molarity, but it would be molarity squared. Right? And I can only get rid of one of the molarities using the rate. And so the units of measurement changes depending on the reaction order, okay? So we're gonna take a look at how that plays out just down here. So I have the example right here. The rate law is K, you don't need to write this down. We just did this for the problem. The rate constant times the reactant concentrations. If we break everything down, we know that the rate is molarity per second. And this is molarity. Okay, so we can skip to this one. Now, if I'm solving for K, what I can do is I can cancel out the molarity on top with the molarity on the bottom, and that's how we got this for the previous example. Now, I did all the work for you, so you guys don't need to recalculate everything, but this is how the units of K, the rate constant, will have a different unit of measurement depending on what the order of the reaction is. If the order of the reaction is 0, that means it's going to be just molarity per second, just a regular. So if I give you an example, it would look like this. Rate is equal to K. And then we know that, let's say, I don't know, random compound, H2. If the reaction order is 0, if I do anything to the power of 0, what does that number turn into? It turns into 1. So that means it would just be K. And so K is just equal to the rate. And we know the units of measurement for rate is molarity per second. So K will also be molarity per second. Make sense? Okay, but let's say, for example, that the reactant concentration is to the power of 1, right? Order of the reaction is 1. Okay. That means what we would have to do for K is, this is going to be molarity. So it'd be molarity per second divided by molarity. Okay, molarity cancels out. What's the only thing that we have left? Per second, second to the power of -1, which is why we get s to the power of -1. So just keep that in mind, that depending on the order of the reaction, the units of measurement will change. So when you're doing FRQs and you're doing calculations for this, I know it's tempting to just put per molarity per second, but just make sure you're very careful with calculating out the units for K, okay? Because you will lose points if you give the wrong units, depending on the reaction order. So just a heads up about that. Please don't memorize this. If you're doing the algebra correctly, you'll just be able to get it without memorizing it, okay? Any questions? You guys ready to try a problem on your own? All right. Okay, so same thing as before. I have the reaction right here. Got some trial data for you guys to take a look at. And what I want you guys to do is I want you guys to calculate out both, or you want to figure out the rate law and calculate the rate constant. Let me actually make it a little bit easier for you. I'll put everything to the same power. So there you go. Okay. So I'll give you guys maybe 5 minutes to try this out. You can work with the person next to you, see if you can get the rate law and calculate the rate constant. All right, guys, so let's do the rate law. Rate law, pretty easy. This one is just going to be the rate is equal to K, and then the concentration of the reactant, which is CH3CHO. And then we don't know the power yet, so I'm just going to write M. So hopefully you got that as your skeleton. Okay. Now, what you want to do is you want to compare this data. See how changing the rate will change, or changing the concentration will change the rate. So let's look at the first one, 1 and 2. How does the rate or the concentration change here? Yeah, times 2. Now, if I multiply the concentration by 2, what happens to the rate? Yeah, it goes up by times 4. So if you look at the relationship of the change, 2 and 4, you can see that the change is double, right? Doubling the concentration will quadruple the rate. And so what will be the exponent right here? Yeah, 2. Okay. Because if let's say I have 2 here, if I double the rate to 4, I need to double it. And so that will get me to 4 and 16. Okay. So we'll quadruple the rate if I double the concentration. Okay. All right. Any questions on the exponent for the rate law? Okay, hopefully not too bad. Okay, now let's calculate the rate constant. Now I'm gonna just do some algebra tricks in order to make it easier. I'm gonna isolate the K by itself. So for the equation, you should have the rate divided by the reactant concentration squared. Okay, so we're just gonna pick one of the values to work with. I'm gonna pick the first one because it's the first one. We're gonna do 2.06. 2.06 times 10 to the power of negative 11, and it's going to be molarity per second, divided by the concentration, which is going to be 1.75 times 10 to the negative 3, and that's going to be squared molarity. Okay. Okay, now let's do the units first. Now, we know that we need to distribute the exponent, right? So I'm going to have to end up squaring 1.75, and I have to, square the molarity. So if I take the molarity out, it's going to be molarity squared on the bottom. So what that means is I can cancel out molarity, and that's going to get rid of one of the molarity. So my unit of measurement for the final answer will be molarity -1 and seconds -1. Okay. And then for your numbers, I just did the calculations already, but you should get 6.73 times 10 to the negative 6. Okay. So if you got that, good job. If you're off by a little bit, not too bad, but just make sure your exponent is correct and the units of measurement are correct. Okay. Okay. Any questions about that problem? Okay, so this next part right here, there's a lot of information, a lot of little details that we can derive from the rate law equation about 0, first, and second order rate or reaction orders. Okay, so I have this table here. Please don't memorize it. Honestly, don't even think too much about it. All it does is it kind of breaks down the information for 0, first, and second order reaction. So you have the rate law. For a 0 order, the rate is equal to the equilibrium constant. For the first order, it's going to just be the equilibrium constant, not the equilibrium, the reaction constant and the concentration of one of the reactants. And then for second order, you just need to square it. So if you guys take a look at all this stuff, and you guys can read more about this in your reading, which everybody does, you guys can get some more information about it. Like I have the units of measurement for you. T1/2 is the half-life. So the equation to figure out how long it takes for half of that concentration to disappear. The integrated rate law is, you guys know y equals mx plus b, right? The equation for a line, a slope, and finding the slope is m. Now we like to graph how the reactant concentration changes over time. And that's going to be the rate law for it. We derived this using calculus. I'm not going to tell you how we got it, but you guys can check the book if you want that explanation. Okay. Now, this is the part that I really want to focus on. Let's actually start with this part right here. Okay, make sure you jot this down somewhere because it tells you what happens in these different reaction orders. So in a 0 order reaction, the concentration of the reactants does not affect the rate. Okay. So it doesn't matter how much of the reactants you have in a 0 order, the rate is always going to be equal to K, the rate constant. Okay. So you can start adding more of a reactant. It's not going to change the rate at all. That's a 0 order. That's basically the definition of a 0 order reaction. Okay. For first order, the rate is dependent on the reactant concentration to the power of 1. So it basically just correlates exactly the same. If I double a reactant, it will double the rate. If I triple a reactant concentration, it will triple the rate. If I quintuple it, the rate will quintuple. Same thing, just keep going down the line. It just stays exactly the same. And you guys don't need to write down the examples if you don't need to. It's just kind of there to help elaborate. And then you guys know already for a second order reaction, the rate depends on the reactant concentration, but squared. Okay, so if I double a reactant, it will quadruple the rate times 4 the rate. If I triple the reactant, I think it's no nuple, you times 9 the rate. If I times 4 the reactant concentration, it will times 16 the rate, and so on and so forth. Yes.
For the second order,
Mhm.
where it says,
Oh, the rate law. Yeah.
how would the slope look like if instead of just having squared it was concentration of 1, concentration of 2? Like anything.
Oh, so yeah, the slopes are going to be a bit different for all of them. So 0 order, the slope is negative k. So just negative the rate constant. Same thing for first order. But for the second order, the slope is going to be just k.
Oh, on the last example,
Mm-hmm.
we had the concentration of NO and then the concentration of O3.
Mm-hmm.
And the rate of each was 1.
Yes.
And it was the second order to be added to.
Oh, good question. So the question was, here this is for 1 reactant, but what if we have 2 reactants, right? How would we draw the line? So we would actually have to do 2 lines on the same graph, because you can't do a line that has both of the reactants in it. So if I had for example, like you're talking about, like if I had a second order by A, B, right? I would have to draw 2 lines. So one of the lines would represent A, and then the other line would represent B. So yeah, you would have to have 2 lines, but unless they really hate you on the test, you're not going to get anything like that. Great question, though. Okay, which is a good segue into what I want to talk about next is the straight line plot to determine K. So we can use a graph representing how the concentration changes over time in order to find K. The K is just a slope. Now I'm going to zoom in a little bit because each one of the reaction orders has a different way of plotting it. So if you guys notice, for a 0 order reaction, the y-axis is the concentration, and the x-axis is the time. So how the concentration goes over time. Okay, and that slope is going to be negative k. That's how you would determine k. Okay, but if you take a look at the first order reaction, what's on the y-axis? Yeah, so ln, so yeah, it looks like natural log of the concentration. It does look like in concentration. So it would be the natural log of the concentration. Yeah, so natural log. Okay, so the natural log of the reactant concentration is plotted on the y-axis versus time. This you will kind of have to memorize because this will come up, the difference between the graphs. And a lot of times when they give you the graph for the problem, you can figure out what the reaction order is to double check your work. If it's plotted with concentration over time, concentration and time, it's going to be a 0 order. If it's a natural log of the concentration with time, that's going to be first order. Okay. And then last but not least, we have the second order one. Second order is 1 over the concentration. So concentration to the power of -1 versus time. And that's going to give you the K. Yeah, this is, like I said, this is where like being better at math will really help you in this class. Yeah, physics too. Just any like graph interpretation, because the way that we get these equations and these graphs is through calculus. So if you have some pre-calc or calc knowledge, it'll be a bit easier to understand. But if not, it'll be a bit harder, but it is still understandable as long as you know how this plotting works. And this is the reason why we learn all that stupid graphing stuff in algebra and algebra 2, because once you start going into the science field, this is the stuff we need to look at and interpret. So yeah, it's not going to help you pay your, I don't know, your phone bill or nothing, but it is helpful for different fields. Okay. Yeah. All right. So let's move on to half-life. You guys probably heard the term half-life in biology before, or on video games. Half-Life 3 will never come out. But half-life is the amount of time it takes for the concentration of a reaction to reach half its original value. So basically, if I have a container that contains, I don't know, like 15 moles of a compound, how long will it take to get to 7.5 moles? Okay, so yeah, that time right there, that is called the half-life. Okay, and then the second half-life will be how long does it take for this container to go to half it. Damn, I can't talk. Half its concentrate, or half the quantity. Okay, so if it goes from 7.5, it'll go to how long it takes to go to 3.25, and then the next half-life will be, yeah, whatever, what, 1.625. Why did I pick such a hard number to start with? Should have just kept it an even number. Yes, 6.5. Thank you. Wait.
No, the one between 7.5 and 3.25. That'd be 6.5, right? So it'd be 3.
No, because this needs to half. 7.5 needs to divide by 2. Am I doing this wrong? 7.5, 7.5.
Yeah, I was like, wait, what?
Yeah, I'm tripping out. But yeah, you get the point, right? The half-life is how long it takes for the concentration to go down by half every single time. Okay, so we have a nice little graph here showing us concentration. So here, the first half-life is going to be how long it takes for the original concentration to go down in half. The second half-life is going to be how long it takes that one to go down by half. Okay. Yeah. All right, so with that, all that stuff, let's kind of put it together. I want you guys to answer 11.11. I want you guys to figure out which one of these four could represent the units of the rate constant K for a reaction that is third order. Okay, so what's the units of measurement for K for a third order reaction? Okay, so try that out, because this kind of unit manipulation will be very helpful as we go forward. All right, you guys ready to go? Kind of, hopefully. Okay,
Yes.
so let's try it out. So if I have a third order reaction, the simplest way to write a generic equation for that is just by writing the rate is equal to the rate constant times the concentration of a reactant to the power of 3, right? Now you could do, you know, the power of 2 times power of 1, but that's just overcomplicated. So if we just look at the units of measurement, let's convert everything into units of measurement. The units of measurement for rate is molarity per second. Okay, we're trying to figure out K, and then we know that concentration is measured in molarity, okay, to the power of 3. Okay, so if I wanted to kind of expand on that, it's the same thing as saying K times m times m times m, right? That's to the power of 3. And then we have molarity per second. Okay, now what we want to do is we want to isolate K by itself. So if I wanted to isolate K, what I can do is K is equal to molarity per second times m times m times m, right? Because we're just dividing by the 3. So far, so good? Okay, so molarity on top is going to cancel out with one of the molarities. And so what I'll have left over is 1 divided by S times M squared, because it's M times M, right? Now we can rewrite this. If I have something on the bottom of a fraction, it's the power of negative whatever. And so we'll have M to the power of negative 2, S to the power of negative 1. And there you go. This is the units of measurement for a third order reaction. Now, here we don't have any seconds, but we can easily convert seconds into minutes, right? And so we can just say that C is the correct answer. Okay, so I know that we didn't use any numbers per se on this one to answer this question, but be comfortable doing calculations with just the units of measurement because it'll actually help you check your answers and it kind of speeds up a lot of the things. Okay. All righty, any questions on 1111? So what we're going to do now is we are going to move on. We're going to jump forward quite a bit and see if we can do kind of a longer question. Okay. You're going, yeah, FRQ. You're going to have this handy, this chart. So just make sure you have it on your Chromebook. I'll have the problem up here and I'll zoom in so it's easier to see, but just make sure you have that chart because being able to use those formulas will be very important. Okay. Okay. We're going to do 11.14. And let's see if you guys are able to try answer this question using the information on the chart. Okay, so we're going to be looking at the decomposition of a certain insecticide in water at 12 degrees Celsius. It follows first order kinetics. Okay, so that should already tell you which part of that table you'll be using. It's going to be first order kinetics. Okay, the rate constant is 1.45 per year, so that we know that the K is going to be 1.45 per year. Okay, the quantity of this insecticide is washed into a lake on June 1st, leading to a concentration. So we have the original concentration. So I'm going to say A0, original concentration is 5.0 times 10 to the negative 7 grams per centimeters cubed. Okay, and then the average temperature does not change. So basically temperature doesn't really matter here. We don't need to concern ourselves with how temperature affects the reaction. Okay, so first part of the problem is asking us, what is the concentration of the insecticide on June 1st of the following year? Okay, so we're going to have some time that goes by. You want to find the concentration of the insecticide after 1 year. Okay, that's what part A is asking you. And then part B is asking you how long it will take to decrease to a specific amount. It's basically asking you to find the mass of the sun or something, huh? Okay, so you have everything that you need on that chart and based on what we learned to solve this. So I'll give you guys about 5 minutes. Try to go through it. If you guys can't finish, totally okay. I know it's a new type of problem. I'm going to go over it with you guys, but I want you guys to kind of wrestle through it. If you guys want to talk with your table partner, you can try to see if you guys can work out a problem or work out a solution, but we're going to go over it in 5 minutes. Okay, so take some time to work it through. Do you need more than 5 minutes?
No, I'm just saying.
Give you the rest of the class, but just kidding. Okay, so let's go over this problem. So here we pulled out a lot of the information together. So the hint that I gave you was that this is first order kinetics, or it's not a hint, but I told you that's first order kinetics. So the hint I gave you was we're going to use that column that was on that chart. So if we go up to first order kinetics, okay, on that chart, that has all the equations. We're only going to be focusing on this column right here. Now, let's take a look at this information that we have here and just some of the stuff that we pulled out. So if I bring up a white screen just so we could see what we wrote down, you can see that we have the information for K, the initial concentration, and we're looking for the concentration after a specific amount of time, right? 1 year. Now, let's take a look at this right here and see if there's anything on this, this chart that has all that information. Now, rate law, we got K, okay, that's good. Units doesn't really matter here. We're not really talking about half-life, right? But if you take a look at this integrated rate law, it has a lot of the information that we already pulled out, right? We have K, we have time, which is 1 year. We also have the initial concentration. A0 means the time at 0. So the initial concentration, and it also tells us that's equal to the natural log of the final concentration, which is going to be at a certain time, 1 year. So this is the equation that we're going to be using in order to solve this problem. So just make sure that you guys are comfortable looking at different equations and different problems, seeing what equation applies to the information we get from this problem. Okay, does that make sense why we're using that equation, guys? Okay, so the equation from the chart that we get is going to be the natural log of the final concentration is equal to negative K time plus the natural log of the original concentration. Okay. Copy that down correctly. Okay, so now what we want to do is we just want to start plugging in our numbers. Now, we are looking for AF, okay, the concentration after a year. So I'm going to just leave that alone for now. Okay, and I'm just going to plug in the values I have. I have negative. The time that I have in the beginning, or the time that I'm working with is 1.45, or sorry, the K that I'm working with is 1.45 per year. The time that I'm working with is 1 year. Plus the natural log, and the initial concentration is this right here. It's going to be 5.0 times 10 to the power of negative 7 grams per centimeters cubed. Any questions so far? All I'm doing is plugging in the info that we got. Okay, let's do a little bit of a housekeeping with the units just so that it's easier to work with as we go forward. Do you guys see anything that can be canceled out? Yeah.
The years.
Yeah, exactly. If you look at years, we have year and then we have per year, which is the same thing as 1 over a year, right? And so the years can cancel out. Okay, which makes sense because we're looking for final concentration, which is some type of grams per volume, and that's what we have left over. Yeah, do you have a question? Okay, so let's do some of the math just to simplify it down. Okay, so negative 1.45 times 1 is negative 1.45. Okay, and then in your calculator, you want to punch in the natural log of this number right here. So if you punch that into your calculator, you should get negative 14.509 grams per centimeters cubed. Okay, everyone get that? Just ln and then 5.0 times 10 to the negative 4. And that's all equal to the natural log of AF. Okay, so what we're going to do now is we're going to start combining some of the values together. So what we're going to do is we're going to do 1.45 plus negative 14.509. And that is going to give you negative 15.959 grams per centimeters cubed. So the natural log of AF is going to equal this value right here. Okay. No, we got to still find AF. So does anyone remember from their algebra class how to get rid of a natural log? It is exponent of what specifically? Do you remember? Great. Yeah, the inverse of ln is you want to put everything to the power of e. That's okay. This is why we're working on math. So e to the power of ln. So if we put this to the power of e, the ln and the e cancel out, and all we'll have left over on the left side is AF. Okay, and then on the right side, we'll have e to the power of negative 15.959 grams per centimeter. And sorry, I shouldn't be putting grams per centimeters cubed there. And then it's going to be grams per centimeters cubed. So if you punch that into your calculator, e to the power of negative 15.959, that's going to give you a final answer of 1.173 times 10 to the negative 7 grams per centimeters cubed. Whew, it's a long one, right? So yeah, like I said, we went from like cross multiplying and fractions, and now we're going into like logarithms. So it gets more complicated as we go forward. Okay, so we're gonna take a 5-minute break, and then when we come back together, we will do part B together. So go to the restroom if you need to, stretch your legs, and then after that, thanks. We'll get into part B.
I was so close.
That's good. If you're getting close, that's a good sign. Alrighty, guys. I think we'll probably finish off with this problem, part B. But let's take a look at part B now, and then yeah, let's see what we're looking for here. So we have a new situation that we're trying to take care of. So why don't you guys just read the problem and try to figure out what variable we're looking for and what the new value is. So write it down on your paper somewhere, jot it down. What are you trying to find in this problem? And what equation should you use? Let's take about a minute, see if you guys can figure that out. Jot it down on your paper. Okay, guys, so for part B, what are we looking for? Yeah, we're looking for time because it says how long. How long is just another way to say you're looking for time, right? So in this problem, you're going to be looking for T. Okay, and it says, how long will it take for the insecticide concentration to decrease to 3 times 10 to the negative 7 grams per centimeters cubed? What variable does this stand for?
AF.
Yeah, AF, or final concentration, right? So the final concentration is going to equal 3 times 10 to the negative 7 grams per centimeters cubed. Now, all the other information is still the same. And it looks like this equation is probably the best thing to do. So here, we're going to be looking for time. So I'm going to give you guys 3 minutes to try to solve out this algebraically. Okay, algebra might be kind of hard, but I believe in you. And so try it out. Try using this equation, this new information that we have, the information we had before, to calculate for time. Okay, and then we'll close up with that. So I'll give you guys about 3 minutes, and then we will go over this in just a second. Okay, so let's plug in the values that we have. Now we know that AF is this value right here. So on the left side of the equation, we're going to have the natural log of A. Why am I doing A again? 3 times 10 to the power of negative 7 grams per centimeters cubed equals, we have K, which is negative 1.45 per year. And then we're looking for T plus the natural log. And our starting concentration was 5 times 10 to the negative 7 grams per centimeters cubed. Okay. All right, so let's plug in our values. For the left side, if you find the natural log of the final concentration, you should get 0.511. Okay, and then I guess I skipped all that. On the right side, you should end up with, sorry, this is if you divide, my bad. So you're gonna wanna move over the natural log right here. You're gonna subtract it from this side. So if I rearrange the equation, I should get a natural log of 3 times 10 to the negative 7 grams per centimeters cubed minus the natural log of 5 times 10 to the negative 7 grams per centimeters cubed. And then that will all be divided by negative 1.45 per year. And that's going to equal time. And then for my value, you guys can correct me if I'm wrong, I end up with 0.352 years. So this is the operation that you want to do. You want to subtract the 2 natural logs and then divide it by the time or the rate constant. That should give you 0.352 years. Okay. Alrighty, so the next time that we meet, we should be able to finish unit 10 on kinetics. And then after that, we'll jump straight into equilibrium. Again, we're not going to be taking the test next week. Instead, we're just going to combine kinetics with equilibrium. Okay.